The broadcast is now starting. All attendees are in listen-only mode.
Welcome to Eccentric Mold and Engineering's webinar. If you're here for a common plastic injection molding design challenges, you're in the right place. I'm Connie and I'll be your host for this session. A few things to cover before I turn over the webinar to our keynote speakers. This presentation is expected to last approximately 30 minutes. Q&A is included, so during the presentation, feel free to submit your questions using the chat function located in the lower right-hand corner of the control panel. If we run out of time, we'll answer as a follow-up to your questions at a later portion of the day. With that, I now turn over our webinar to our keynote speakers, John Sidorowitz, Glenn Miller, and Darwin Rowe. Gentlemen, please tell me a little bit about yourselves.
Thank you, Connie. This is John Sidorowitz. I am the VP of Inside Sales and Customer Service here at Eccentric Mold. Been with the company for nearly 9 years now and dealing with plastics for the last 15 years. Darwin?
I'm Darwin Rowe, Senior Project Manager here at Eccentric. I've been with the company for about a year now. I've got 25 years of designing and building this.
Glenn?
Hi, I'm Glenn Miller, tooling engineer. I've been with Eccentric a little over a year and a half. I have about 25 years of mold design and build experience.
All right, perfect. Just wanted to thank everyone for joining this afternoon. Got kind of the topics that we're going to kind of go over for today's webinar. Covering thin walls, rads and transitions, draft, threading on plastic parts, overmolding, micromolding, tight tolerances, ribs, and bosses. So we'll kind of jump into it here.
Let's start off with our thin walls and wall thickness in general. It's very important that you maintain a uniform wall thickness. Anytime you have a part that goes from thick to thin, back to thick again, you tend to get pinch points in areas where the plastic isn't going to flow well. So always be cognizant of maintaining a nominal wall thickness on your part when you can.
Okay. Yeah, and if you've got questions, feel free to submit them during the webinar. And if something's relevant, we'll try to answer it as we go. So on this slide, we've got some recommended wall thicknesses for some of your more general plastics. Just something to keep in mind. So radii and transitions. So when designing, you really don't want sharp corners. Sharp corners are going to cause molded in stress from the resin flow. By creating rads and corners especially, it's going to allow material to flow easier throughout the part. And this also helps maintain a consistent wall thickness. If you do have areas where you need to move from a thick section or to a thin section or vice versa, you want to practice some of the methods that we've got there. Not do a hard stop with a 90, but kind of a gradual shift from thick to thin. And again, this will minimize the molded in stresses within the part.
And that goes for anything, whether it be a rib or a transition, as John said. Anytime you can add radius to any of these sharp corners, it will definitely help.
Someone asked if these slides will be available later. Yes, they will. They'll be sent out, I think, within 48 hours of the webinar.
They will be online at our website.
Okay. Next is draft. It's pretty important.
Really, your bare minimum draft is a half a degree. And of course, on our end of it, anytime we can get more than that, 1.5 degrees to 2 degrees per side is a standard practice for designing parts. And then if you're going into parts that have texture, depending on what that texture is, heavy stipple or whatever, 3 to 5 degrees, and sometimes that can go a little more depending on what the texture is and how deep it is.
Right, and then keeping in mind on how that tool or the part is going to be built, and that will dictate your your draft directions and everything else. Even for pulls, actions, side actions like that, you want to have them drafted so those actions can be easily pulled during the demolding process.
Drafts and radiuses both go the same. Like for molding, the larger the radius and the larger the draft, the easier it is to mold the part for filling in ejection.
Right. All right. Threading. So we do quite a few parts with threading, and we see a lot of problems when customers are moving from metal parts to plastic. Any threads that were designed originally for metal, it may not translate to plastic. Plastic threads need to be designed a little bit differently than metal. Smaller threads we can make use of.
Overmolded inserts.
Yeah, exactly.
Yeah, you get down to the smaller sizes, anything from a 1/4 down and smaller. It's always an option to either do molded in inserts or even do like heat staking and so forth to get those threads in the part for you.
Correct. And just a note, plastic male threads are designed to connect to, a metal female thread. Don't use plastic female threaded connector to a male thread connector. These type of joints will almost always break or leak.
As you can see from that picture, you're going from a steel thread, which is going to have sharp roots and crests, and a plastic part, those are going to be more rounded. So sometimes you're going to find, as John said, there may be fit issues and leakage. It might be a little loose or a little tight. You're going from plastic to steel, so there's going to be a little work on that.
Right, and then the other thing, just when designing the threads, try to avoid knife edges or feather edges. Include radiuses wherever you can, and keep a uniform wall thickness to minimize stress. So, sharp edges again can be stress concentrators. Sorry about that. So this leads us to overmolding. These are just some general guides for overmolding. When designing a part that's going to have an overmold, treat each part individually as its own separate part. You want to have a nominal wall thickness across both parts, depending on the material for each, the substrate, the first shot, and the overmold, which is the second shot. You want to at least meet the minimum requirements for wall thickness for the material that you're using. And just, again, treat each part individually and follow the best practices for designing for injection molding.
The same thing goes for the overmolded material as it does the substrate. You want to avoid any sharp corners, any blunt transitions. You always want to use good radiuses and transitions whenever possible.
And then rads, you can use them creatively to kind of break up the substrate in the overmold. Creating hard shutoffs between the two, so you get a clean break between the overmold material and the substrate.
You've got some good examples there in the images on the screen
right.
To the right.
So it's kind of using that groove, and then working in and on how the part's going to be gated. With overmolding, you really don't want to see the gate vestige, typically on the rubber piece or the secondary piece. So try to utilize pass-throughs or anything like that kind of in the middle picture where we gate from inside the part and feed the plastic out. And then it also doubles as a mechanical hold as well.
And that's another key right there is designing your substrate with mechanical holds that will help the overmold material adhere to the plastic part.
Okay. And, going back to the rads, kind of using the accent groove that we got there for creating the hard shutoffs. if you have a good clean shutoff and a good design substrate, that it's going to make for a much better overall part.
Right, and your substrate dictates a lot. If your substrate's warped, twisted, anything like that, it's going to pose problems trying to fit that to the overmold, which can create issues trying to fill this material without flashing over or shorting parts out. So your substrate's obviously key to running a good overmold.
Okay, micromolding is the next topic. This is something we don't really do here at Eccentric, but just wanted to bring it up. It's micromolding is, I guess, different for everyone depending on their capabilities. What we consider a micro part is any part that weighs less than a gram. Feature size, we don't really accept parts with features smaller than 10 thousandths, and even that's iffy. So just when you're considering, rapid manufacturing, it's difficult to get parts this small made, 3D printing and rapid tooling. So just keep that in mind when designing. Excuse me. So tight tolerances. Again, this is something that's kind of thrown about loosely. If not performed correctly, a tight tolerance part can lead to part failure or performance. So if you do have a part that's critical with some tight tolerance features, you want to look at utilizing low shrinkage materials, avoid tight tolerances in areas around alignment of the mold halves. Notice parting lines or any moving components such as slides or actions that might be on the outside of the part, and design your parts to avoid areas where you may have warp.
Right.
That could affect the tolerance.
Any kind of flat part, thin wall without a lot of structure, that part's going to tend to warp and twist a little bit. So you really have to be cognizant of your design.
All right, next we're going. Oops, sorry. Go ahead.
Go ahead.
So ribbing, a lot of customers have or come to designs with very thick part sections. This is where you want to core out and kind of introduce ribbing back into the part. It's going to allow for strength and stiffness within the part, and reduce the weight and overall keep the integrity of the design. So whenever you're designing a rib, I mean, the common rule is to make it about 60% of the adjoining wall thickness.
Maximum of 60%.
Yes.
Always try to shoot for less than that, obviously, but
right.
Depending on the material.
Yeah, and how deep the ribs are in draft, that could play a factor. And what this does is eliminates the risk or minimizes the risk of sink marks on the show surface opposite side of the rib. If you're dealing with glossy materials like a polycarbonate or acrylics or something like that, that'll tend to show more. So you may want to reduce that rib thickness down to maybe 40% of the adjoining wall thickness. So,
and be aware that that anytime that the taller the rib, the greater the chance of issues molding, sticking,
fill.
You want to have some draft on those ribs. Straight wall drafts just are a no-no. You really have to have some draft on there to pull that out. If you got significant draft on it, then you can go taller with the rib. The taller the rib, the more structure. So it's just a balance there of your design.
All right, bosses, similar to ribs. They're used for locating, mounting, and assembling parts. When designing them, your wall thickness of those ribs or bosses and the height are going to be the biggest factors that you want to look at. Just a quick calculation. The wall thickness around a boss design feature should be about 60% of the nominal part thickness, if that thickness is less than 1/8 of an inch. And then the height of the boss should be no more than 2.5 times the diameter of the hole in the boss.
You've got some good examples there of of what a good boss design would be and what would be a less favorable. As John said, the 2.5 times the diameter. Anytime you can add a chamfer or connect a boss to a sidewall with another rib instead of the other two pictures to the left there where it's connected right in, you can see where the part would be much thicker and the propensity for sink is going to be much higher in that area.
Okay. That kind of brings us to the end. I don't know if anyone has any questions or anything for us. I know that was kind of a brief overview of common challenges, but yeah, we're open for questions.
Okay, so we do have a question here regarding tolerances.
What about tolerances of form, cases that require transitional fit, cylinder with tight control on warp and roundness? I'm not sure what that
Tolerances of form, just
mating, like a friction fit?
of mating parts that need to be a tight fit.
Yeah, I'm not sure how to answer that one. I'm thinking it might be almost like a friction fit. Yeah, if you could clarify if you asked that question.
Any other questions?
Okay.
Okay. We have no other questions for this afternoon. With the individual about the tolerance question, okay, he did reply back. Thank you.
What can be done to improve form in the part, reduce warp?
Warpage issues can be design in rib structure, things like that to help your part maintain its flatness and its shape, or
Material
change.
process. So yeah, there's a lot of factors that'll go into warp. It's really looking at the design and what you have and seeing how it's warping and how that can be, addressed. Even, cooling fixtures, which we usually advise against, have worked in the past. But yeah, it's really going to be design dependent on how to tackle that for parts.
Material's a big thing.
It's like adding strength ribs and stuff to keep it from twisting.
Non-filled, filled materials, so forth.
Included roundness. So yeah, I mean, gating could be part of that. It's difficult to answer.
Okay. Well, that'll wrap up our session for today. Thank you for joining this webinar. For any questions or interest in Eccentric products, please visit our website, social channels, or contact us directly at the number or the email listed on your screen. We actually have one more question. I apologize here.
All right. I know uniform wall thickness is always recommended, but in which cases is possible to reduce the thickness for maintaining a small size product?
Well, it's more the overall thickness of the part. It can be thin wall, depending on the material you're using. But again, all of the general rules do come into play with ribs and bosses and sink and all of those things. So if you have a thin walled part, as long as you have a material that'll flow through a thin wall, usually we can process through that. It's really a part-to-part basis in the material you're using.
Right.
Okay, well, that'll conclude our webinar today. Thank you, everyone, for joining us, and we hope you have a great day.
Thanks, everyone.
Thanks.